So this is a really unusual paper. It doesn't describe any system that we've built. There are no experimental results. In fact, I think the best review was the program committee review, which basically said, we don't quite know what to do with this paper, so we'll accept it. So thank you. What this is about a way of thinking about the systems that we build, about what we are creating. It's a little more philosophical in character, but that's okay. Once in a while, it's useful to take a step back and think about what we're doing. This is a paper written with two colleagues, Wei Gao, who's over there, who's a faculty member at the University of Pittsburgh. If you haven't met him before, please say hello to him. And Brandon Lucia, who unfortunately couldn't make it. He's a colleague at Carnegie Mellon. So all of you, some just a few years ago, others like me, many, many years ago, remember learning about a diagram like this in high school or maybe freshman college, right? This is obviously the periodic table of elements. What is amazing about this is that it contains so much information distilled into just the structure of this table. It's over 100 years old. It took a few decades for people to figure out how it should be organized and how to do it right. In fact, early versions of the table were created before people even knew the difference between atomic weight and atomic number. Right? That had to wait for the discovery of nuclear structure in the early 20th century. In spite of that, imperfect as it was a useful data structure. To represent this data structure today might take a few hundred bytes, few kilobytes, that's it. So how has this kind of table been useful? It's been useful in explaining the behavior and properties just by the position of an element on this table. You can tell a lot about it. What happened? Okay. Early versions of this table had big gaps. And presciently, people who looked at it said, you know, I suspect that this means there are some elements that we don't know about. And using this table, guessed what those properties of those elements might be and used it to find the elements. And most interestingly, nature, of course, gave us only 92 elements. This has up to another 26 elements, which are man-made, and you're able to fit them all in. So this is an example of, this is the inspiration for our work. Is there a way to take what we're doing and distill it into a form that has both predictive value and explanatory power and helps us look to the future and think about this? Now, let's be very clear. You know, our field is a synthetic field. Unlike nature, for which we don't have the source code, we create the system. So we know at a source code level what the heck we're doing, at least we hope. So I'm not, you know, don't draw the analogy too strongly. It's a weak analogy, but useful analogy. The closest example I have to something that we're trying to do is think about Moore's law. It's really not a law of nature in spite of its name. 50 years ago, it was an astute observation about empirical data pertaining to progress in the semiconductor industry. The amazing thing about it is it has almost been a self-fulfilling prophecy that has brought us a long way. So think of what we're trying to do as closer to that. Is there a way to think of what we're doing and distilling the knowledge that we have into a form that's likely to be very useful? I want to emphasize the last point on this slide, that as I mentioned, the periodic table took, 30 years, 40 years to evolve. So I make no claim that what I'm presenting today is the last word on the subject. Rather, I hope it is the first word. It's a kicking off a conversation in our community about how to think about the systems that we built. So let me summarize in one slide the critical insight. The critical insight is it appears, at least to the three authors of this paper, and I hope by the end of this talk, many of you as well, that a tiered model of computing appears to have the right attributes to describe the systems that we have today. Okay, hopefully it'll come back, and gives us explanatory power as well as predictive power. And I'll show you a few examples in a few slides. The critical insight is that at any tier, there are a set of design constraints that dominate attention. And I'll show you what those constraints are in just a few slides. Regardless of who designs the system and what secondary optimizations they do, all of them have to respect these design constraints. And therefore, it forces much greater similarity. Whether Microsoft makes it, or Apple makes it, or Amazon makes it, or Google makes it, all of their components at that tier have similar attributes. Okay? Second, that major shifts in computing, the shift from time sharing to personal computing, from batch processing to time sharing, from the world we have today to the emergence of edge computing, which is happening before our eyes, all of these things are typically marked by the appearance, disappearance, or repurposing of one of the tiers of computing. Okay? I want to contrast and make clear that the tiers that I'm talking about and the tiered model is a very different way of thinking about the systems we build from the well-known hourglass model. So all of you know this. The best example of the hourglass model is the internet. You have a small handful of protocols, IP, TCP, DHCP, DNS, right? Probably on the fingers of two hands, you can capture all of the necessary protocols, and they sustain, at last measure, I believe it was a $21 trillion T economy, which is the scale of the internet. Okay, it's amazing. Now, the essence of the hourglass model is interoperability. If you follow this API perfectly, then there's almost unlimited innovation on both sides of the API. And that's a very useful way of looking at the world. And I'd like to suggest that there's a different way of looking at the world which has a different set of merits, and that is the tiered way. So a key point here is that there's no expectation of interoperability when we talk about tiers. So if you pick one entity, say Microsoft, it has at the cloud tier components, it has at the edge computing tier components, it has at the mobile computing level tiers components, and so on. They interoperate with each other. So at each level, there is a presence. However, if you picked a random component from Microsoft and tried to mate it with Apple, it's not going to work. Okay? So this was the state of the world until quite recently. So on the one hand, you had various devices, desktops, which have been around since the 1980s, laptops, which became popular in the 1990s, and smartphones, which appeared mid-2000s. 2007 was when the smartphone came into being, but there were prior versions of these devices that were called PDAs, without the phone functionality, even before. And then you had the cloud, which today is represented by cloud providers, but also things like Dropbox, which store your data, keep it safe, and give it back to you when and where you want it. So from this world, there's a new world emerging. Okay? This is what the world looks like, much more complex. The cloud is unchanged. It's virtually the same cloud that we've known and loved or hated. Your sentiment about it is not going to be changed by the emergence of the other tiers. We have now, instead of just desktops, laptops, and smartphones, many, many more devices, especially wearable devices, HoloLens, Google Glass, various versions of those, wearable smartwatches from Apple, right? All of these things. You have things like drones, about which you heard talks earlier in this workshop, and various kinds of sensor arrays. Some of them are mobile, some are static, etc. So this is the IoT world. So the mobile and IoT world is the third tier in this picture. Edge computing, which is emerging, is represented by tier 2 here. Okay? And then there is another world, which actually has been around for at least 10 years, but its significance has exploded and continues to rise, which is tier 4 are devices of which RFID tags are the most well-known example, which have no chemical energy source. They have no battery. Okay? They harvest energy and use that for computing. And I'd like to suggest to you that today and in the near future, thinking about the world in these 4 tiers is a very valuable way to think about the world. And the next big change in the computing landscape will arise when we perhaps add another tier, or one of these tiers disappears, and so on. So what are the salient attributes at each tier? At tier 1, you have infinite amount of computing. So compute elasticity is one of the attributes. The second is storage permanence. If something is really precious to you, no matter where you capture the data in the other tiers, you preserve it in tier 1. And hopefully, the chances of you retrieving it a decade, 2 decades from now is highest at tier 1. Last but not least, tier 1 is where the cost per unit of computing is the lowest, thanks to consolidation. So unless there is a compelling reason for you to do compute in one of the other tiers, you preferentially do it at tier 1. Tier 3 is the next easiest to appreciate because it is all about mobility. The devices have to be light, they cannot dissipate too much heat, they have to have long battery life, they cannot be too big, etc. All of the constraints of mobility apply. And sensing, very rich sensing, is also part of this world. Now, IoT devices, some of them are not mobile, but they still have to be cheap. And the cheapness often suggests that both because of reasons of mobility or cost, offloading computation to tier 2, which is the edge at low latency and high bandwidth, is valuable. So network proximity, which is the bandwidth and latency between tiers 2 and 3, is the crucial attribute of edge computing. Notice emphasis on network proximity. This is not necessarily physical proximity. I could use a fiber link. I could have low milliseconds, few milliseconds latency and high bandwidth, even with a cloudlet that's 50 kilometers away. Last but not least is tier 4. I guess Shyam Kolkata is not at this workshop. He's not here. Maybe one of his students is. Anyway, he exemplifies the kind of work in tier 4. Also, my colleague Brandon Lucia, who couldn't come. Deploying tier 3 elements has been now since 2000. People have been trying to create sensor networks. At the end of the day, in spite of all the grandiose visions, the biggest pain has been changing batteries. Especially if you're trying to drive costs down, having to change batteries is a nightmare. So the vision of tier 4 is something that you can leave for 50 years, like an RFID tag. If you come back and you happen to have the right frequency incident radiation, you can read the tag. So there's a tremendous amount of work at that level. My last slide, one of the interesting insights about the tiered picture is maps almost exactly to considerations of energy. Okay? So on the x-axis here is the sort of absolute aggregate energy. On the y-axis is a fuzzy metric, not to scale, but it roughly characterizes how hard it is. How much do you have to sweat about energy at that level? If you run a cloud data center, total aggregate energy is of the order of megawatts. You work very, very hard to try and keep the total energy footprint of your systems modest. You try to load balance. You try to make sure that you do not have hotspots, right? So a lot of attention paid to energy. At tier 4, energy harvesting is the name of the game. So it's dominant. Similarly, at tier 3, on mobile devices, battery life dominates. It's only at tier 2 that life is easy. Okay? The paper has a lot of things that I don't have time to talk about. There's a brief history of how, starting in the 50s, did these tiers evolve and appear to this final form that we have today. Of course, it's not final. It continues to evolve. There's some thoughts about the future. And finally, the driver at the end of the day seem to be 3 very basic things: space, time, and energy. And if you think in those terms, the evolution of those tiers makes sense. So I hope I've convinced you that there is value in thinking about these things from a very basic point of view, that a tiered model seems to fit the present and the past pretty well. And again, I want to emphasize that it's the discussion that I hope this leads to and the evolution of these ideas that'll be the biggest use of your time and mine. Thanks.